Now that we've learned multiple different transformations, like translations, reflections, rotations, and you just learned about dilations, making shapes bigger and smaller, now we can have multiple shapes look the same and have some things about them be exactly the same, but these are going to be called similar shapes. Similar shapes are multiple shapes that look similar but are different in size. So it's just one is bigger or smaller than the other. There's an enlargement or a reduction. Same shape but different size means a dilation occurred, and the symbol is that little squiggly, and this should say size. So make sure that says size. Does order matter when writing similarity statement? And what does the order tell us? And yes, it does matter. The order tells us which angles are equal in measure and which side lengths are proportional. So let's get to some examples. Since triangle ABC is listed first, that is my original. The triangle listed second is my image. So I'm going to follow these multiple choice steps and see which one of them takes my original shape to my image. So a translation of left 2 units, and just like we did with congruent figures, we only need to pick one point. So point A will map to point N. So all the moves I'm going to do is just with point A. So 2 units to the left and 4 units down gets me right here, and that is the point -6, -4, then a dilation of 2, which means I need to multiply this by 2, so I get -12, -8 as my point, which would be way out here. That is nowhere near point N, which is where I want it to be, so that is not going to be the answer. So first it says take a dilation of 1/2, which puts me at -20. Then I go to the right 2 units, and then up 4 units, and that puts me right there. Well, I should say A prime, which is not on N, so this is also not the correct one. I should first say, since ABC is my biggest one, and it's my original, and I'm getting smaller, I have a scale factor less than 1. So everything that has a scale factor of 2, which was this first one right here, a dilation of 2, that one automatically is out because my shape is getting smaller. So I'm looking for just my dilations of 1/2. So let's try this third one. So a translation of right 2 units and up 4, that puts me right here at the point -2, +4. Then a dilation of 1/2. So if I take half of both of those, I get -1, 2, which puts me right on point N, and A maps to N, so that's how we can tell that this is the correct transformation and not this last one. In the example above, okay, so right away I should also be able to tell there is no reflection, okay? So there's not going to be a reflection because my shapes are facing the same way. In a reflection, your shape changes its orientation of where it's facing. So I ruled out rotation and reflection because the two triangles are facing the same direction. With a rotation or reflection, the shapes face a different direction. So here, ABC is listed first, so I'm going from small to big. So my scale factor should be larger than 1. So everything with a dilation that is smaller than 1, I am going to cross off. And my shapes are facing the same direction. Therefore, there's going to not be a reflection or rotation of any kind. So that leaves me with just these two. And since A and D are labeled first, that means A maps to D. So let's work through our 2 examples and see which one is the correct one. So a translation of 3 to the left and 1 down. So if I take A and go 3 to the left and down 1, negative 1, 2. And then a dilation of 2, which means I have to multiply those points, each coordinate, by 2, which gives me negative 2, 4. Negative 2, 4 leaves me on D, so that means this is the correct translation for this picture. So here I'm going to take A, and it maps to E. So here's A. It goes to E. A, B, C, D is listed first, so that's my original. So I'm going from big to small. So my scale factor should be greater than 1. So all the ones with a dilation of less than 1, I'm going big to small. So my scale factor should be less than 1. So all my dilations greater than 1, I am going to cross off. And that's just that one right there. And I see that my shape is flipped over, so there's going to at least be some kind of reflection or rotation here. So let's figure out which one. So if I follow along on this first choice, it says first I'm going to reflect over x equals negative 1. Well, the line x equals negative 1 is that dotted line right there. Point A is 1 to the right, so if I reflect it over, I go 1 to the left. There is my reflection, and that is the point 0, 3. And then a dilation of 1/3, so I have to multiply those by 1/3, and I get 0, 1, which puts me right on E. So this very first option is the correct transformation of the shapes. So looking at these again, J, K, L, M is my original, which is a small shape, so I'm getting bigger. So my scale factor should be greater than 1, since I'm going from small to big. So all the ones with a dilation of less than 1, I'm going to cross off. I can cross those off because I know my shape is getting bigger. So I'm going to highlight point J, and I want it to go to point P because both are listed first. So let's start with this third option, a reflection over y equals 1. Well, the line y equals 1 is right there. And J is 3 units above, so if I reflect over that line, I need to go 3 units below that dotted line, which puts me right here. And that gives me the points negative 3, negative 2. And then a dilation of 3, so I need to multiply those coordinates both by 3, and I get the coordinates negative 9, negative 6, which puts me on point P. So this is, in fact, the correct transformation. So the effect similar angles have, or similar shapes, I should say, the effect on angles is that when you have two shapes that are similar, corresponding angles are equal in measure. You know which angles are equal by the order in which they are labeled. Again, order matters in which they are labeled. So A is going to be congruent to A. So I have this small triangle outlined in blue, and then I've got this bigger triangle outlined in purple. Angle A is in both triangles. Angle D in my purple triangle is up here. And then in my blue triangle, since B is listed second, that is going to be equal in measure to angle D. So if angle B is 45 degrees, that means angle D also has to be 45 degrees. And then E is listed last, and E is a 90-degree angle. C is also listed last, which is also a 90-degree angle, so proving that all angles in similar triangles are equal in measure depending on where they are labeled. Side lengths are a little bit different because they are not equal in measure, but they are proportional. You do have to use the scale factor. So here we have a scale factor of 2. We're going to go from the small to the big. So triangle, it says ADE is the image of ABC. So ABC, we're going to multiply those by 2, and we get triangle ADE. Now that means triangle ADE is twice as big. So so I have a side length of 3 here for BC, and then a side length of 6 here for DE. Image over original equals 2 over 1, or just 2. So the scale factor is also the proportion in which the sides should be labeled. So the side lengths are proportional. They are the same proportion as the scale factors. So explain our reasoning of why these two triangles are similar. Well, first of all, I have vertical angles, which are congruent. Okay, these should be parallel, but we're not given that they're parallel, so we can't assume. So let's look at MN. Side MN is 2. Side PQ is 3. So image over original. Since MNO is listed first, that means it's the original. Triangle PQO is listed second, so that is the image. So my scale factor should be 3 over 2. Now if I look to NO, so segment NO is 1, 2, 3 is 4 units. So that's 4 units. And then side length QO is 6 units. Now, Q to O is in the image, so 6 goes on top. Over the original, let's reduce this scale factor, and we get 2/3. Since both scale factors are equal in measure, both are 2/3, that means the two shapes are similar. So all the angles, angle P is going to be the same length as angle M. We have 90-degree angles there. So those two shapes are similar because their side lengths are proportional. Their corresponding side lengths are proportional. Now, looking here, which two triangles are similar? Well, here I see that I have flat 90-degree angles, and I do not have one in that triangle. So right away, this triangle is out. Now, our side lengths, again, need to be proportional. Side length of 4, side length of 4. Here I have a side length of 2, side length of 2. And in JKL, I have a side length of 2 and a side length of 4. So right now, we should see that this last triangle we did is not going to be proportional to the other ones. So this triangle is out. So if ABC is our original, EFG is going to be our image. 2 over 4 reduces to 1/2. And you can see, since both of these side lengths are the same length and both of these side lengths are the same length, that shows you that triangle ABC is similar to triangle EFG. I had to be careful how I labeled those because, again, order matters, because angle A is going to equal angle E, angle B is going to equal angle F, angle C is the same measurement as angle G, and they are similar because the corresponding side lengths are proportional.